Alright, if you haven't already got out your fan club worksheet, please do so, because we will be working through that together on your worksheet today with this problem. So the problem states, when Sam found out that teen pop sensation Cali, Colorado was going to be the guest of honor in their town's fall parade, he almost freaked out. He was Cali, Colorado's #1 fan. On the night of the parade, Sam arrived early and staked out a spot on the street right next to the parade route. Sam first spotted Callie when she was 87 feet down the street, and her car was moving at a speed of 6 feet per second. When she passed in front of him, Sam was only 20 feet away from her. He let out a big scream. So let's make sure we have all the information pulled out and understand what it represents on our picture to the right. So the first bit of information is that Sam first noticed the car when the distance down the street was 87 feet. So at time 0, that distance down the street was 87 feet. Also in here is that 20 feet away is where Sam will be when she comes in her car crossing right in front of him. So that represents that portion of the graph. So let's look at number 1. When Cali, Colorado was 87 feet down the street, that was at when Sam first noticed her. Her visual distance from Sam was actually about 89.27 feet, and let's explain why. So if we think about what the visual distance is in our diagram, it looks like it's right there. Sam would be looking that direction, so that's visual distance versus distance down the street here. So 87 feet is that distance down the street, and so I hope at this point you're noticing that if I have an 87 feet distance this direction and a 20 feet distance this direction, we have a Pythagorean theorem kind of relationship. Then use those two leg lengths to find the hypotenuse length, which happens to be the visual distance here. And that comes out to be 89.27 feet. And so you would need to take a moment, maybe after the video is done, to explain why that is the case. Number 2. We are to complete a table to describe the given distances with respect to the time in seconds since Sam first spotted Cali, Colorado, and then we're going to sketch a graph of visual distance as a function of time. So we have our times along the left-hand side. Some of them are missing in the distance down the street. Those are we're going to fill in, and some are just missing in the visual distance. So we have to remember in the original problem the car is traveling at a rate of 6 feet per second. So let's think about how in the beginning that 87 feet was given in the problem. How did they come up with 81 feet? Well, after 1 second, the car has traveled 6 feet. So that means the car would be 6 feet closer to Sam as far as the down the street measurement is concerned. And the same thing is going to happen. We can continue to take 6 feet away here and get 75. 81 subtract 6 is 75. Then we have 75 subtract, looks like that subtract 12. Well, that's because we have had 2 seconds that have been changed here. From 2 to 4 is 2 seconds difference. So we have 12 feet traveled. Same thing from 4 to 6, 12 feet traveled. Same thing from 6 to 8, 12 feet traveled. And now, from 8 to 11, we've got 3 seconds, which means we should have 18 feet traveled, 6 times 3. And finally, the 87 subtract the 12 times the 6 is going to give us the 15 feet at time 12 seconds. So let's think back to what we kind of talked about in number 1 as far as the visual distance is concerned. Definitely a Pythagorean relationship. So the way I'd like to show you is using our stat lists a way that maybe you haven't used them before. So if you go to Stat Edit, you usually have used these lists to make a scatter plot of data, but you can use it, in addition to that, you can use it to calculate things for you. So I put in list 1 all my times. You can't see 12 because you'd have to scan down a little bit. But in list 2, I want to put in my distance down the street. Well, I can put in a formula in my L2 to tell it what to calculate. So that formula that we used to calculate essentially was we took the original distance down the street and subtracted the rate times the time to get the distance down the street. So I can put this formula right in there, and you'll need to know how to find the L1 because that will pop the times in, substitute it for you, and that's under second step, L1. So once you put that in, once you put the equation in list 2, you can push enter and it's calculated all of those distance down the street for any time you put in there. That's helpful. It's especially helpful, I think, when you go over and tell it to do this Pythagorean relationship in list 3, because that one is a more labor-intensive process. So I'm going to highlight that list 3 and I'm going to put in the equation essentially that we are using. We are using the distance down the street as one of those leg measurements, if you'll remember, and the time was, the 20 feet that Sam is from that direct distance there is 20 feet. So if you put in square root of that L2 squared plus 20 squared, you're doing the Pythagorean theorem. And again, you would get the L2 by doing second stat and picking L2. So if you push enter, once that formula is in there for you, it will calculate all those values, as you can see at the bottom of the page. Very nice. 89.27, 83.43, 77.62, 66.10, and so on. Alright, let's continue number 2 a little bit. Since we have the data in our lists, I'm going to use a scatter plot and hopefully clarify what's going on. So if you use second y equals, you get this plot menu. And I want you to enter on the first screen and you get this, which has the plot 1 off, and I'll leave that on. It has the correct scatter plot I'm interested in. We're going to have to talk about these X list and Y list. We have to tell it where to find our domain and our range values. And so if you'll remember, we were trying to sketch a graph of the visual distance as a function of time. That means time is our X list, and if you'll remember, L1 was where our times were at, and our visual distance is supposed to be the Y's, or the range values. So our visual distance was actually in L3, because remember L2 was our distance down the street. So I want L3 in there, and I can put it in there by again using second stat and choosing L3. So make sure you have the stat plot on, that it's the scatter plot, that we have list 1 and list 3. The marks don't matter. And if I zoom mine, I get this representation. And that kind of almost looks linear. And that is actually a bit deceiving, because if you instantly think that it's linear, in fact, we're going to find out that it's not a linear relationship in the end. So I wanted to pull out the key at this point. You should have everything in your table filled out. You should have, at this point, maybe a little bit of a sketch until time 12, because remember, we just have the scatter plot until time 12. And notice over here what's going on. On the key, it has this function going from decreasing to increasing again. That's definitely not a linear relationship there. So let's figure out why this is as we do some other problems and why that happens. Okay? Number 3. We're supposed to write a linear function to relate time and distance, and then we're going to use it to determine when Cali, Colorado was directly across the street from Sam. So as you can see, there's the 14.5 in my table. Let's see how that goes. Most of this should be already in your mind. The way we calculated the distance down the street was using this linear relationship, taking the original distance and subtracting the rate times the time. And so if we realize that the distance down the street will be 0 when Cal is directly in front of Sam, we can solve for time and get 14.5. So if I kind of go back to the thought about how our graph is going to come back and increase a bit, let's think about what's happening at time 16 seconds. Well, if I use our formula, the distance down the street would be 87 subtract the rate, 60 per second, times 16 seconds, and I get a negative 9. Negative 9 feet. So let's think about what that might mean. So at 14.5 seconds, the car with the star in it is directly in front of Sam. So after that, you'll be looking at the back of the car, and they're considering that we are 9 feet to the left of where Sam is standing, if you think visually. So let's think about visual distance then. Remember our relationship? We could put the distance down the street squared and the distance Sam is in the vertical direction and square root it, and we get 21.93. So that to me means we've come closer, closer, closer until the distance is 0, and then the distance starts to increase again because the car has passed by, and now that distance is increasing again, that visual distance. And so that's what happens here. If we look at our 14.5, that's where the distance was 20, the lowest we can go here, visually distance. And then at 16, we're kind of rising again, and we'll continue to rise from that point on. Alright, number 4. What function rule can be used to find the visual distance between Sam and Callie in terms of seconds? Okay, this should not be too awfully hard to understand at this point either. The only thing with this key that I will note is that we have this visual distance with time, and then they put this X in there, and they shouldn't have done that. It should say visual distance with time as an element, and this should be 87 minus 6t there squared. And that's what we were doing. We were calculating the distance down the street squared plus the 20 squared all underneath the square root. So we've been doing that all along. So number 5 says use this function to complete the following table. So we have 2 functions now that really, if you'll remember, are in our lists, in our stat lists. So we can go back to our stat list now. Instead of calculating these each individually, we can use them to calculate for us. This one says 87 minus 6 times list 1. This one says square root of list 2 squared plus 20 squared. And we can calculate those in a fraction of the time that would be required to calculate otherwise. Again, remember, I purposely put this in here to remind you all when you're doing your notation that if I have something as a measurement of time, I want t as my variable on the other side. Number 6, do your answers in point A make sense in the context of the problem situation? So point A says we have a negative time, a 117-foot distance down the street, and a 118.7 feet visual distance. Well, let's think about what that negative time might be. That negative time might mean that that's before Sam actually noticed that Cali, Colorado was driving towards him. so maybe 5 seconds before, and the distance is greater than that initial distance that we were given in the problem, and the visual distance is greater than the initial visual distance. So sure, yes, that would mean that 5 seconds before Sam spotted Callie, her car was 117 feet down the street. Number 7. Do your answers for point D make sense in the context of the problem and situation also? And what do they represent? Point D says at time 34 seconds, we have a negative distance down the street and a visual distance of 118.7 feet. So let's remember when Cali, Colorado crosses right in front of Sam, and that's at 14.5 seconds. So this is nearly 20 seconds later here, which would mean that the car is to the left of him, and so that distance down the street would be represented with a negative for that reason, because the car is already passed by, and the visual distance is still a 118.7. So yes, it could mean that 34 seconds after Sam first spotted Callie, her car was 117 feet down the street in the other direction. Alright, number 8. What restrictions, if any, must be placed on the domain of this function? So we'll first have to think about what the domain is of this function again. The domain is time. So will it matter if we have negative times? No, it just means before Sam spotted Callie. Could we potentially go on forever and ever? We could. We could. So I would say there are no restrictions. It could be all real numbers for the time. What about in the real situation? The domain and range really have some restrictions, like is often the case. So let's think about what we're measuring in the range. Again, we know in the domain we have time, and in the range we have a visual distance. So let's think about how the closest that Sam gets to Callie is 20 feet. So we're definitely not going to be below 20 feet as far as the distance that we are visually. But on the other hand, that time kind of potentially would not go on forever and ever in either direction, because Sam might get tired of standing there after the parade has ended, or Sam didn't arrive till a certain point when the parade started, and so on. So there are restrictions upon real world situations.